Thank you very nice thank you very much for the introduction and for the organization of this nice conference. Here I will present recent advances in thermal noise magnetometry of magnetic nanoparticle ensembles, which was a subject of my PhD, and I actually defended it about 17 days ago. So I have been pursuing this research at the Ghent University in Belgium and at the PTB in Berlin. And I hope that at the end of the talk, I can convince you that noise is not always disturbing and unwanted, but that we can actually use it as a signal, that it actually can be very useful as well for us as scientists. And the object of interest today are magnetic nanoparticles. They consist of a magnetic core with a non-magnetic shell, and they have sizes in the nanometer range, and they can be manipulated by magnetic fields. And this makes them very interesting for biomedical applications. So there they can be used as heat sources, as imaging objects, or as drug carriers. But the prerequisite for their usage is that we characterize them precisely. And most of the conventional magnetic characterization technique, they measure their response to an external excitation, which is often a magnetic excitation. And this external excitation can actually alter the state of the particles. They can, for example, form chains along the magnetic field lines. And I have a small video here which illustrates this very nicely. Without any external field, they're nicely dispersed, but when you apply a field, you can see that they start to form these chains. And this definitely influences their magnetic behavior, their magnetic properties. So in this case, our external excitation already alters the outcome of such a characterization method. And to overcome this limitation, we have been developing thermal noise magnetometry, which is a characterization technique that doesn't need any external excitation. So if we consider a nanoparticle ensemble in the absence of any external excitation in thermal equilibrium, we can measure its magnetic signal. And one would think that we won't measure anything, but that's not completely true because of the thermal energy in the system. The magnetic moments of these particles are constantly changing direction, and we can actually measure this as very tiny fluctuations on the magnetic signal of the particles. And from this stochastic time signal, we can calculate the power spectral density. And this tells us at which frequencies, which processes are taking place, and we can relate this to the properties of the particles. And this characterization technique is called thermal noise magnetometry. It's a relatively new technique. And yeah, my supervisors were the first ones to use this for magnetic nanoparticle ensembles at room temperature. So during my PhD, I've been developing this technique further, and I've been looking into experiments, theory, and simulations. And one thing you should notice here is that these experiments are not so easy to perform because there are very, very tiny signals. So we need very sensitive magnetic field sensors and a very nicely magnetic shielded environment. And that's why we have been collaborating, or why I've been pursuing my PhD also at the PTB in Berlin. They have a long-standing experience in both of these subjects. All right, so a little bit more about this power spectral density. It has the shape of a Lorentzian. So if you plot it on a log-log scale, it's flat until a certain cutoff frequency, and then it falls off with 1/f². And this cutoff frequency is inversely proportional to a fluctuation time tau. And there are two fluctuation mechanisms. So if the particles are in suspension, they undergo Brownian motion, and therefore they rotate as well. And this gives rise to Brownian fluctuations. But the moments can also fluctuate in the particle, or in the frame of the particle itself, in the energy landscape defined by the anisotropy of the particles. And these are Néel fluctuations. There is a second important parameter here, which is a noise power, so the prefactor of this power spectral density. And there are two ways to calculate this noise power. Firstly, by calculating the variance of this stochastic variable. So you can calculate this from the probability density function here. And secondly, you can also calculate the noise power by just integrating the power spectral density over the full frequency range. And this noise power is an important parameter because it gives a measure of how strong these fluctuations are. And since we're working with tiny signals, this is actually an important parameter to consider. So first thing I've been doing was investigating the influence of sample parameters on this noise power. And as we can expect for stochastic signals, the noise power scales linearly here with the number of particles in our sample and quadratically with the volume of our particles. And if we combine those two effects, we have a situation which is very, very similar to a situation where magnetic nanoparticles cluster. So there is a decrease in the number of fluctuators and an increase in their volume. And in this case, we saw that the noise power actually scales with the volume of the particles. And this is very different than deterministic characterization techniques where you apply a field, because in this case, there won't be any amplitude dependency, or at least not to first order. So thermal noise magnetometry is intrinsically sensitive to these clustering events. And then I would like to continue with the question, what happens with the thermal fluctuations of magnetic nanoparticles when we increase the temperature? Well, typically people answer this question by saying that the fluctuations will be stronger, but the answer is actually a little bit more complex, and we have to break down this answer in considering the effect of temperature on the fluctuation time, so the shape of this Lorentzian, and the effect of temperature on the noise power itself. If we take a look at the fluctuation times, temperature here enters in both of the expressions. So if we increase the temperature, the fluctuations will be faster, and therefore our fluctuation time decreases and our cutoff frequency in the power spectral density increases, so goes to higher values. And that's indeed what we see from our simulations. Just the effect in the Néel fluctuations, it's much stronger because of this exponential in the expressions. And then if we take a look at the effect of temperature on the noise power, we have to take a look at the probability density function of our magnetic moments. This probability density function for Brownian fluctuations is uniform, so the moment is equally likely to be found anywhere on this unit sphere. But in case of Néel fluctuations, there is actually preferred direction along the anisotropy axis of the particle. And if we increase temperature, the moments will deviate further away from this anisotropy axis. And this also results in a different behavior in our dependency of noise power on temperature. So in case of Brownian fluctuations, our noise power is independent of temperature, but in case of the Néel fluctuations, our noise power is dependent on temperature, and actually its dependency depends on which field component we are considering and what is the orientation of our sensing direction with relation to the anisotropy axis. We've also measured nanoparticles at different temperatures around room temperature. I'm sorry for the degrees Celsius here, but it's room temperature up to 50 degrees Celsius. And both nanoparticle systems, they fluctuate under Brownian fluctuations. And it's actually quite surprising here because the area under the curves is not conserved, while on the last slide I told you that the area should be conserved for Brownian fluctuations, but for this simulations are very useful. So we simulated these nanoparticle systems as well. And if we unlock this higher frequency range here that we cannot measure in our experiments, we see that our curves actually cross each other, and that the area under the curves is conserved after all. And I also want to draw your attention to the rather large dependency on temperature. So here we plotted the value of the power spectral density at 8 Hertz as a function of temperature, and there is quite a large dependency. So in this case, nanoparticles or the noise can be used to estimate temperature differences in the local environment of our nanoparticles and use the nanoparticles as a local temperature probe. And then I want to spend a few more words about these thermal noise magnetometry measurements. So for most of my measurements, I have been using this SQUID setup. It's a very nice setup with a high sensitivity and a large bandwidth, and excellent low frequency shielding because we have been using a superconducting shield here. But the system requires liquid helium, so we also have a limited sample space, and it's not transportable, not very flexible, and we have to fill it 2 times a week with liquid helium. And this is actually me filling the system about 3 weeks ago. And I might be smiling here, but it's a very time-consuming thing to do. So that's why we have been looking into alternatives. And we have constructed a tabletop setup for thermal noise magnetometry, which is based on OPMs, optically pumped magnetometers. And these are sensors that don't require cryogenic cooling. So this is how the tabletop setup looks like. It's more or less 1 square meter in area. Has a few magnetic shields of mu metal, and then here you have the sensor, and next to it our magnetic nanoparticle sample. And we have confirmed that we can use this tabletop setup for thermal noise magnetometry by comparing it to the SQUID setup. So we measured 2 nanoparticle systems in both setups, and as you can see, the paraspectral densities, they agree very nicely. So we can actually use this tabletop setup for TNM measurements. And that's what we did. We have used it to monitor magnetic nanoparticles in a biological environment. And these results you can find in the paper here. And that brings me to the conclusion. So personally, I think that the strength of TNM really lies in its simplicity. With this, I don't mean that these experiments are easy, but that they're very easy, simple. So you only need a sensor, actually. And we're not interfering as an experimentalist with anything. We just passively look at the fluctuations. So there's no excitation. This means that we have a setup with low complexity and a very stable measurement environment. So we could, for example, use TNM to monitor a sample over several years. And we also have an unbiased measurement, so no influence of any external excitation whatsoever. And then I would like to end with a quote from George Gershwin, one of my favorite composers. I frequently hear music in the very heart of noise, and I'm very happy to answer any questions as well.
Well, first of all, Katrijn, congratulations on your PhD. And thank you very much for your amazing talk. Do we have questions from the audience? I have one. Okay, I'll ask mine then. I'm the lucky one. Okay, so to consider the Brownian motion and the Nell motion, it all depends on the media you are considering, right? From if you change the media, changes everything. So how do you take that into account?
Yeah, so those 2 fluctuation mechanisms, they exist next to each other. And it depends on the particle properties and also the media indeed, which fluctuation mechanism is dominant. So if your particles are larger, generally there are only these Brownian fluctuations, and they need to be in a suspension for this as well, indeed. Once the particles are immobilized, you only have the Néel fluctuations.
But then you're always comparing them in the same media, or?
Yes, I've been measuring only samples in a suspension liquid. Yeah.
Okay. Okay. Thank you very much. Yeah. I think due to the time constraints, we should go to the next one. Thank you very much, Katrijn, for your talk.
Thank you.
And